Welcome to the Deep Dive, where we sift through the latest research to give you the knowledge you need fast. Today, we are going deep into the molecular world. AI is finally learning to speak the language of chemistry.
It is, yeah.
But this isn't just about language, it's really about geometry and physics. We're looking at how these models are now being built with rotational symmetry, just, baked right in.
And that's the critical distinction. For an AI to really master something like drug design, it has to get past this one huge hurdle, rotational symmetry.
Okay, what do you mean?
Well, if you take a molecule and just spin it around in 3D space, a traditional AI sees a completely different input. It gets confused, and that leads to some pretty inaccurate predictions.
So the model is basically wasting its time relearning the same molecule over and over again, just from a slightly different angle.
Precisely. And our sources are all pointing to this really elegant mathematical solution, these advanced frameworks, specifically spherical equivariant graph neural networks, AGNM.
AGNNs.
Yeah. And these architectures have the rules of physics, the rules of rotational symmetry built directly into their design. They guarantee that if you rotate the input, the molecule, the prediction will transform in the exact, correct, predictable way.
So they're, structurally engineered to obey physics? That
Yeah.
sounds a lot more reliable than a model just learning from data.
It is. I mean, we're talking about models that respect the symmetries defined by, what mathematicians call the SO3 group.
Right.
And for high-fidelity modeling of, complex biological systems, that level of physical accuracy is just non-negotiable.
So here's our mission for this deep dive. We'll start by unpacking that core concept of symmetry, then we'll get into the math, which has the surprising quantum mechanics flavor to it. And after that, we'll switch gears completely and see how these powerful, reasoning-focused LLMs are tackling chemical logic puzzles like retrosynthesis. It's a really cool dual approach. Okay, let's unpack those two essential concepts that seem to be behind all of this geometric AI stuff: invariance and equivariance. What's the simple distinction we need to grasp?
Right, they really are the cornerstones. So let's start with invariance. It's the simpler idea, really.
Okay.
It just means a function produces the exact same output, no matter how you turn or move the input. Think about the potential energy of a molecule just floating in a vacuum.
Right.
You can rotate that molecule 10 degrees, 180 degrees. Its internal energy doesn't change one bit.
So invariance is about protecting the molecule's core identity. Things like its energy or its mass, right? No matter how it's oriented.
Exactly. Now, equivariance, that's where the real magic happens. And it's what these advanced GNNs are built to achieve.
And that is?
Equivariance means that if you transform the input, the output transforms in a predictable way. So if you rotate the molecule, any related physical vector, like, say, the direction of a force acting on an atom, has to rotate in the exact same way.
That makes perfect sense for physics. I mean, if I'm modeling a force pushing north and then I rotate my whole setup 90 degrees, the force vector I get out at the end has to be pointing east.
It has to.
But why is that so hard? Why is rotational equivariance the big challenge here?
Well, GNNs handle shifting things around translation pretty easily. But enforcing strict rotational equivariance in 3D, that SO3 challenge, you have to fundamentally change how the network even sees spatial features. It's crucial because molecular behavior is governed by these conserved quantities from quantum mechanics like angular momentum that follow these rigid rotational laws. If your model breaks SO3 symmetry,
it breaks physics.
It breaks physics.
Simple as that.
And this is where it gets really fascinating because to enforce this symmetry, these EGNNs are borrowing tools straight out of advanced physics. Instead of standard coordinates, how are they actually representing the features?
They completely ditch standard vectors, which, look different every time you rotate them. Instead, they represent information as something called spherical tensors.
And that is the key architectural shift. Think of it like this. Instead of trying to map 3D space with, clunky squares and lines from a Cartesian grid, you're using spheres that naturally fit the problem. It's like using a globe instead of a flat map to navigate the Earth.
You're using a geometric language that inherently gets rotation.
Correct. These spherical tensors are special because they transform according to what are called irreducible representations, or IREPs, of the SO3 rotation group.
IREPs.
Think of IREPs as the primary colors of rotation. They're the simplest, most fundamental rotational building blocks. You can't break them down any further.
Wait, SO3 group irreducible representations? That sounds like a serious amount of computational work.
For those of us who, don't do quantum mechanics for a living, what's the simple way to think about how the model makes sure everything spins correctly?
It's all about making every single step of the calculation rotation-proof. They use two main mathematical tools. First, spherical harmonics.
These are used to project your normal 3D vectors into these special spherical tensors. They're basically the guaranteed method of translation, making sure that when an atom spins, its feature representation spins perfectly with it.
And the second tool, that's for when the different features actually meet each other.
Right, that's the Klebs-Gordon decomposition. When the model aggregates information, say, multiplying two spherical tensors from neighboring atoms to create a new feature, you get this geometrically messy, complex result.
Ah,
The Klebs-Gordon coefficients act like a high-powered mixer and strainer. They immediately strain that messy product back into its simplest, rotationally clean components, its irreps.
that's a great metaphor. So it sounds like you're building a model that has to pass a physics exam before it's even allowed to make a prediction. The physics can't get lost at any step.
That's a perfect way to put it. This whole machinery builds what are called equivariant kernels, and they're guaranteed to transform correctly. And that translates directly into better predictive power for really high-fidelity 3D modeling.
Okay, so let's look at what this sophisticated physics-first modeling actually enables, starting with drug discovery, predicting binding affinity, how well two molecules stick together.
This brings us to a model called GES. It's a graph neural network that's been enhanced with language model embeddings. And the sources show GMS was designed to fight this huge hidden problem in the field, data leakage.
And let's be clear, data leakage is basically when the model cheats, right? It's trained on data that's too similar to the test data, so it just memorizes answers instead of learning the actual principles.
That's spot on. In datasets like PDB-bind, which is very widely used, it turns out that a lot of the reported high performance was because the training set had complexes that were almost identical to the test set.
So it wasn't really learning.
No, it wasn't generalizing. So the researchers behind TMS needed a truly blind test.
And what was the fix?
They created something called PDB-bind clean split. It's a rigorously filtered dataset. It removes any training complexes that have high structural similarity and a similar binding affinity to the test set. It forces the model to learn the real physics.
And what happened?
The result was striking. When GMS was trained on this clean data, it only performed well if the protein nodes included these contextual features from language models like ESM2 and ANKH.
Wow, that's fascinating. So even with perfect 3D geometry from the GNN, the model still needed the language context from the LLMs to figure it out. It was forced to learn actual biology, not just memorize shapes.
Absolutely. And moving beyond just prediction, this geometric approach lets you do de novo design, designing from scratch. Take RF diffusion 3. It's a diffusion model for generating totally new protein structures that interact with things like drugs or nucleic acids.
And the sources say RF diffusion 3 is being used for things like designing cysteine hydrolases, these complex enzyme. Why is it being good at that?
It's all about fidelity to the small details. A lot of older models would simplify things, use coarse graining. RF diffusion 3 models, all polymer atoms explicitly.
Every single one.
Every single one. For designing an enzyme where that precise geometric fit with a tiny substrate molecule is everything, you just can't simplify. Modeling every atom makes it much more effective for conditioning the model on the exact atom-level constraints you need for a functional design.
And to train a model that complex, you need data that's just as high fidelity. Tell us about this PEPI database. What makes it a gold standard?
PEPI is just invaluable. It's a collection of 329 high-quality protein peptide complexes. But it's not just the structures, it's the depth of the data. It pairs these high-res structures with full thermodynamic data, experimental measurements for Gibbs free energy or day up, but also enthalpy, HH, and entropy.
Why are enthalpy and entropy so crucial? Why not just measure G, the final energy?
Because DG tells you if the binding happens, but DH can tell you why it happens.
Ah, the driving forces.
Exactly. Understanding the enthalpic drivers, bond formation, electrostatics, versus the entropic ones like the release of water molecules. It lets you build models that understand the fundamental forces behind binding. And that's essential for designing drugs that work reliably across different conditions.
Okay, so we've been focused on this physics-first approach, building geometry and symmetry right into the model's architecture. But what happens if we ditch the 3D structure and instead turn to models trained purely on the language of chemistry?
A totally different approach.
Let's switch gears and look at large language models. We know they're great at writing, but can they actually reason like a chemist?
Well, that's the exact question the ChemiQ benchmark was designed to answer. It tested LLMs on core organic chemistry concepts, but using short answer responses, which is much more like how a real chemist would solve a problem. It's not just multiple choice.
And the difference between the reasoning and non-reasoning models was huge, right?
Stark doesn't even begin to cover it. The LLMs with reasoning modes built in, like Gemini Pro 2.5, they got between 50 and 57% accuracy on ChemIQ. The models, without that reasoning component, they were stuck down at like 3 to 7%.
Wow.
And critically, performance went up the more reasoning budget you gave the model, the more computational steps it had to think.
Which suggests it's not just matching patterns in text, it's actually applying a sequence of rules. So what are some of the most advanced chemical tasks these LLMs are cracking now?
Two really complex ones stand out. First is NMR elucidation. Gemini Pro 2.5 was able to correctly generate the SMILE string, the chemical structure, for about 90% of molecules up to 10 heavy atoms, just from reading a full suite of NMR spectra.
That's like solving a high-dimensional puzzle without ever seeing the final picture.
It is. And the second task is IUPAC naming from SMILE strings, which, believe it or not, previous models were terrible at, like near-zero performance. Systematic naming requires following this very rigid hierarchy of rules, and the reasoning models are finally getting it right.
And what about the most demanding task of all? Retrosynthesis. Predicting what you need to make a target molecule. How do we know the LLM isn't just looking up reactions it's seen before?
Well, in the retrosynthesis task, the model doesn't just give you the predicted reactants. It's also required to provide a specific chemical validity assessment and a chemical rationale explaining its decision.
It has to show its work. Can you give us an example of that self-critique?
Absolutely. The sources have a great one. The model correctly flagged an attempted bocamine deprotection reaction as invalid for a certain target, and its rationale was perfect. It said the target atom was a tertiary amide nitrogen, and that reaction only works on primary or secondary amides.
So it identified a logical impossibility based on the rules of functional group chemistry.
That's the difference right there. It's not just recalling information, it's applying rules and finding flaws in a proposed plan. That is critical chemical reasoning.
So what does all this mean? We looked at two very powerful but very different approaches. On one side, you have the physically principled EGNNs, all about perfect symmetry and geometry. And on the other, you have these LLMs mastering chemical intelligence and self-critique.
The future is combining them. The next generation of molecular science will merge these two forces. We're moving beyond models that just see pixels or text toward architectures that are built to obey physics and can then articulate their reasoning like a human expert.
A powerful combination.
It promises faster, much more reliable design cycles for everything from drugs to new chemical syntheses.
An incredible trajectory, but let's connect this back to that ChemIQ benchmark. There was a small detail in there that stuck with me. Even the best reasoning LLMs still sometimes struggle with really fundamental tasks, like reliably parsing SMILE's notation, basically just counting carbons correctly.
Right, the basics can still trip them up.
So here's the thought I want to leave you with. If these models occasionally fail at the basic structural grammar of chemistry, how confident can we really be in the subtle chemical rationales they provide for much more complex tasks, like NMR elucidation or synthesis prediction? What unseen errors might still be lurking in that reasoning chain when the fundamentals aren't 100% solid? Something for you to think about.